evening, and welcome to the Scientific Adventures of Beardman. Today we're on our second episode of astrophysics. We looked in our first episode at telescopes and how those can be used to aid us in collecting light, and that light is the only thing we have to study the universe. So today we're going to look at one of the main ways that we analyze light. And that has to do with, where does the light come from? Well, most of the light in the universe comes from hydrogen. As you can see, 73% of the universe is hydrogen, about 25% helium, and the other 2% everything else. So, when we get light from space, a lot of it came from hydrogen. So understanding how hydrogen gives off light is going to be essential to understanding the light that we get. It's also helpful to know what we get from helium and other elements as well. But we're going to focus on hydrogen since it's 73% of our universe, and it's one of the main things that we use to determine a lot of stuff that's going on in space. So if we look at light coming from hydrogen, one of the ways we would analyze that is to say, what color is it? Okay, well, the color of light is determined by the frequency of light, and the frequency of a photon of light is determined by the amount of energy it has. So the question comes down to, what energies of light, what energies of photons can an atom of hydrogen give off? Well, to understand that, we need to go back to our chemistry and remind ourselves of the Bohr atom. Okay, this is our basic quantum mechanical structure of the atom, with the energy levels defined as circular orbitals in the Bohr model. That's not correct, but the idea of the energy levels is correct. So let's take a look at that. So we got our inside energy level 1, that has the least energy. And as we pull away from that, the energy levels get more and more energy. Remember, that's just like gravitational potential energy. As we lift a ball higher and higher away from the Earth, it has more energy. When it's closest to the Earth, it has the least energy. When the electron is closest to the nucleus, it has the least energy. As we pull it away, it gets more and more energy. Now, one of the issues that quantum mechanics discovered is that energy can't just be any amount of energy, not at that small level. At those level of significant digits, the energy can only have certain values. Okay, and that is energy level 1, can't be anywhere in between there and 2, energy level 2, and so on. So now, what happens if we have something like a star, where the gas is so hot that it's ionized, meaning the electrons have separated from the atom completely? Well, if an electron gets near a proton, they're still attracted, and if they were moving slow enough, just because that particular molecule of gas is moving slow enough, it would fall onto the atom. As it fell, it would release energy and give out light. That moving charge, you can think of it this way, that moving charge would cause a magnetic field, electric field. It would give out light. Okay? So as that electron falls onto the atom, it gives off light. Well, how can it fall? What energy levels can it fall to and through? Well, any two gaps in our hydrogen energy, in our Bohr model of the hydrogen, any two energy levels that could fall from one to the other. Okay? Now, as we go away, the energy levels get progressively closer and closer. So we have a whole series of energies that could be given out as energy level falls from 2 to 1, from 3 to 1, from 4 to 1, from 5 to 1. Okay? That's actually called the Lyman series, and it's in the ultraviolet range, so we won't be paying attention to that because we want to deal with the things we can see and understand better. So astronomers would use all of these energies of light. Okay, but we'll focus on the one in the visible range, and that's the electrons falling from 3 to 2, from 4 to 2, from 5 to 2. That creates what's called the Balmer series, and the Balmer series is in the visible range. If we take those energies, the energy gap between level 3 and level 2, between level 4 and level 2, and we use our E equals HF equation, and we convert that to a frequency that the light will have, because the electron loses that much energy, the photon will have the amount of energy that the electron lost. Okay? So if we take that amount of energy that the photon has, use E equals HF to convert that into a frequency, we can figure out the color of the light that is being produced. Okay, well, since it can only be certain colors, if we were to look at a spectrum of this light, most of the colors, most of the frequencies would be missing. It's only those particular ones that matched up with the gaps in the Bohr model of the hydrogen atom that would actually have light. And there's 4 of them in the visible range. We can see that here. We call that an emission spectra. Okay? These 4 wavelengths of light are produced by electrons falling down energy levels on a hydrogen atom. Now, a definition of emission spectra would be bright lines or bands or continuous spectrum of electromagnetic radiation emitted by a source. In our case, in our specific example, our source would be hydrogen, and it can emit these particular bright lines of the spectrum. Okay? So when we point our telescope at the sky and we see these bright lines, the light comes into the telescope, we separate it with a prism, and we see these 4 frequencies of light, we know that we are looking at glowing hydrogen. Okay? Now another situation could arise. We could have something that's producing all the colors of light, and that light could come in through a cloud of cold hydrogen, and as it came through, the wavelengths, the frequencies that had the correct amount of energy that matched those gaps in hydrogen, those wavelengths could be absorbed by the hydrogen as the electron popped up in energy level, and therefore those wavelengths would be missing from the light that reaches Earth. So if that happens, we get the other thing that we see here with these dark bands where hydrogen has absorbed the light, okay, and all the rest of the light made it through because hydrogen was unable to absorb it because there wasn't an energy gap that matched that amount of energy. We call that an absorption spectra because it is the light that hydrogen is absorbing that we see missing from this spectrum. So a definition of that would be the dark lines or absence of light in a continuous spectrum caused as the light passes through a cold gas. Okay? So that can let us know about things that exist in the universe like the atmosphere of a planet. If the star of that planet was on the opposite side of it and the light passed through the atmosphere of that planet, well then we can see if hydrogen is in that atmosphere, or if other compounds and chemicals, each of which has their own unique signature, their own unique absorption spectrum. And so then we can see not only gases that are hot enough to glow, which give off an emission spectra, but ones that are able to absorb it, which are called absorption spectra. In the next video, we'll take a look at this and see how we use this at the most distant reaches of the galaxy to understand what happened near the beginning of the universe. And this will also take place because we can time travel. So join us next time as we time travel back to the beginning of the universe and see what was going on. You know, just because why not? So we'll see you next time. Enjoy the spectra of light that you're able to see. See you next time on the Scientific Adventures of Beardman.